Last session I was talking about the surface and internal quality in continuously cast product. Actually it will be surface, subsurface and internal quality, because whatever subsurface defects are there in the cast product, whether it is bloom, slab or billet, during rolling they will come to the surface. So, that is those are also important. So, it is basically surface, subsurface and internal quality issues which should be looked into and which are very important for getting a good final product. Now, I mentioned that basically types of products, types of defects and the influence of chemistry, role of segregation, strength, ductility of the solidifying shell, the cast structure, what is the distribution of the dendrites, what are their sizes, columnar, vis-a-vis, equiax, then the influence of casting parameters, these are very important. All these issues will be taken up one by one. Then I talked about the different types of molds which can create mechanical strain on the solid shell, whether it is a curved mold, whether it is a straight mold. If you have a straight mold, first the shell has to be bent, the strand has to be bent and then it has to be straightened. So, accordingly you have sometimes at the inner radius, surface on the inner radius, some type of stress, at the outer surface radius a different stress. These are, if it is like in the bender it is something, straightener it is just the opposite. In case of curved mold it is only the straightener which is coming into play, because the strand itself is coming out in a curved fashion, because from the curved mold. So, you need not bend it, only thing is you have to straighten it, you have to make it horizontal, that is what is necessary here. So, accordingly what are the type of stresses or strains on the shell? These are important because the strain will have to be withstood, it is necessary to withstand the strains, otherwise there will be crack formation. Then I have mentioned that unlike continuous casting, the shell is under continuous movement, it is not fixed. So, and a lot of stresses are getting into the shell. So, first is from the liquid that there is a what is that called, ferrostatic pressure, it is called internal pressure or ferrostatic pressure from this liquid column. So, that is important not only in the mold, as we are going down the stress is increasing, ferrostatic stress is increasing, ferrostatic force is increasing, the pressure is increasing. So, that we have to take into account this. And then when the stress the strand is coming out of the mold, then the shell is increasing in thickness, but just when it is coming down, the shell is not very thick. So, there is a possibility from the internal pressure to bend it, and there has to be some support. So, there are rolls, this one, these are the rolls, and in between the two rolls there is a possibility of bulging, this is called bulging. And in between the rolls you can either use water spray or air mist spray for secondary cooling, because primary cooling is within this mold, but there has to be a secondary cooling to take out of the heat from the liquid steel, so that solidification can continue, and finally solidification is over at this point of time. So, your internal stress, that means the internal pressure from the ferrostatic pressure is valid till solidification is over. Then I talked about what are the different types of imperfections in cast product, blowholes and pinholes. Then there can be crack, there can be depression in certain grades, there can be oscillation marks. I had mentioned that mold is under continuous oscillation. So, there are certain marks on the surface of the shell, surface of the cast product. If they are not very deep, they are okay, they are not taken as defects, but sometimes they are very deep. It depends on the types of oscillation, depends on the type of steel which is being cast. Then there can be segregation. So, these are all defects, cracks, depression, deep oscillation marks, segregation. So, these are influenced by three major issues: the casting process as such. Under the casting process, basically we are talking about the casting speed and the superheat. We are talking of the powder characteristics, it is very important. Today I will discuss how the powder characteristics will influence the mold heat transfer, the primary heat transfer, primary cooling in the mold, how the powder characteristics are going to influence that. Then there is a situation called mold lubrication, because this powder, it is getting melted, and there is a, it is coming inside the between the gap between the shell and the mold, and it is giving some lubrication, that is very important. So, the characteristics of powder also influence lubrication, the oscillation pattern also influence lubrication, these are important. Then of course, the mold oscillation frequency and the amplitude, these are important. Secondary cooling, that means beneath the powder, mold, beneath the primary cooling, we are cooling by either water or mist. So, what is the intensity of cooling, how it is changing from top to bottom, these are important. Then SEN configuration and submergence are very important, sub-entry nozzle. What are the port size, what are the port shape, circular or elliptical, what are their angle, all these are important. Then steel grade is very important, because how it is solidifying through delta ferrite or through austenite. These will dictate what are the strength and toughness of the shell, where the delta to gamma transformation takes place during solidification, or before, at the early part of solidification or the later part of solidification or after solidification, these are very important. These will dictate whether the casting will give rise to sticking or depression. The depression or sticking tendency, this depends on the specific steel grade. Then as I mentioned, the high temperature strength and ductility of the shell is important. Trace elements, sulfur, phosphorus, boron, aluminum, nitrogen, these are very important as far as segregation is concerned. Then caster type of alignment, I have talked about whether it is a horizontal, whether it is a vertical mold or whether it is a curved mold, that will dictate what are the magnitude and distribution of strain on the solid shell. Then I talked about why blowholes and pinholes are created. Basically, it is due to the high content of soluble oxygen, nitrogen and hydrogen. So, if you know this amounts, you can find out the partial pressures of hydrogen, nitrogen and carbon monoxide, and finally, when you add these three, the total pressure, if it exceeds the atmospheric pressure and the ferrostatic pressure, then you have formation of gas bubbles and blowholes and pinholes are generated. So, the whole idea is to restrict the content of soluble oxygen, nitrogen and hydrogen, so that you do not get blowholes and pinholes. Now, today I will be talking about what is happening inside mold. The proper continuous casting I will be starting today. That means, the first heat transfer for solidification starts in the mold. So, it is called primary cooling. So, what are the issues, what are the factors which control the heat transfer in the mold? I will be discussing those issues. I have told that liquid slag which is forming from the powder, after melting of the powder you get liquid slag, which first forms on the top of the liquid surface in the mold, that is near the meniscus. But due to the mold oscillation, this liquid slag which has formed on the top of the mold, top of the liquid steel in the mold, on the top of the liquid steel you have liquid slag. Now, this liquid slag gets drawn into the gap between mold and solid shell. This happens because there is oscillation of the mold. If you look at this here, this mold is getting oscillated in vertical manner, this way. Because of this, whatever liquid slag is forming here, it gets drawn inside because of this oscillation. This is very much necessary because this controls heat transfer, this controls lubrication. So, that is why without oscillation you cannot do continuous casting, unlike ingot casting. Continuous casting, in continuous casting, oscillation of the mold is a must, and because of the oscillation, this slag will get drawn inside this between the gap between the mold and the solid shell. That is why I was talking about this liquid slag is getting drawn in the gap between mold and the solid shell. So, what is happening? The part of this slag it is freezing in contact with the cold surface of the copper mold. Please try to remember that copper mold is getting cooled with water. Inside copper mold there are channels through which water is passing. So, the whole idea is to cool the copper mold, then only heat transfer is possible. Now, in contact with the cold surface of the copper mold, the liquid slag whatever gets squeezed in between the gap of the mold and the solid shell. So, part of it is getting frozen, that means it is becoming solid. So, try to remember what is happening. One part is liquid which is in contact with the hot shell, and one part of it which is in contact with the mold, it is frozen, that means it is solid. So, this relative thickness of the solid vis-a-vis the liquid slag layer in the gap between mold and solidifying shell, this is what is important. This controls the heat transfer. So, please try to remember that in between the gap between the mold surface and the solid shell, there is a layer of, first there is a layer of solid slag, and then in contact with the mold surface, cold mold surface, you have a layer of solid slag, and then you have a layer of liquid slag in contact with the hot shell surface. So, the relative thickness of this, because you can easily understand, more solid shell you have, more solid slag layer you have, more will be the heat transfer. More will be the heat, yeah. So, heat transfer is, that is why dictated by what is the relative thickness of the slag layer, that is what is important. So, this controls the heat transfer. Now, this relative thickness, it is dependent on what? It depends on the, obviously it depends on the powder characteristics. What are the constituents there in the powder? Powder is basically what? You have some calcium oxide, you have some alumina, you have some silica, you have some calcium fluoride, you have some sodium oxide, you might have some small amount of barium oxide. So, all these will determine what is the solidification temperature of the slag, what is the viscosity of the slag, these are very important. So, this basicity of the slag and the solidification temperature of the slag, they play a very important role in controlling the relative thickness of the solid vis-a-vis the liquid slag layer. Now, high solidification temperature, try to understand what is happening. High solidification temperature means the solidification of the liquid slag is taking place relatively earlier. So, you have relatively thick solid layer, and high basicity, it facilitates crystallization of the solid layer. The solid layer initially it is a slaggy in nature, okay, it is a slag type, but then this basicity of the slag, basicity of the powder, this facilitates, higher the basicity, crystallization, there will be a layer, part of the layer becomes crystallized, part of the solid layer. So, both of this will lead to lower heat flux. So, what is causing lower heat flux? Relatively thicker solid layer compared to the liquid layer. If you have thicker solid layer, there will be lower heat flux, because the heat will be conducted faster. So, high solidification temperature and high basicity, these two characteristics of the powder, two characteristics of the mold slag, they will determine the heat flux. Higher the solidification temperature, higher the basicity, lower will be the heat flux. That means relatively less amount of heat conduction will be. This is very important. So, another important issue is the formation of air gap. Then why this air gap forms? Because whenever the solid shell, steel shell, from liquid steel you are after during solidification you are having solid shell, and it is slowly increasing in thickness as you are coming down. So, during solidification there may be a shrinkage, there is expected to be a shrinkage. So, basically there are two forces, I will discuss this later on, the the from the liquid still, which is called the ferrostatic force. It tries to push the solid shell towards the mold, and the shrinkage due to solidification, due to cooling of the shell, it will try to take the shell away from the mold. So, there are two opposite forces. It depends which force is more. If the shrinkage force is more, then you have shrinkage. If the ferrostatic force is more, then you have the shell trying to get in touch with the mold. That means it is a type of different type of thing, different type of issue. So, whether there will be shrinkage or there will be sticking, it is the other one is called sticking. That means the solid shell will try to stick towards the mold. So, if there is a shrinkage formation, then there is a air gap. Air gap means air is insulation, it acts as insulator. So, you have lower heat transfer. So, this is very important. So, heat transfer is basically controlled by the powder characteristics, what are the solidification temperature, what are the basicity, they will determine what is the heat flux, and if there is a air gap, in case of some of the grades you have shrinkage, then you have formation of air gap, and consequently the heat transfer also will be affected, becomes lower. Now, let us try to see how the initial stage of solidification is taking place. The initial surface of the shell, it is forming just below the meniscus. Then what is necessary is the controlled shell growth. Shell should grow in a controlled manner, then only you have a good cast quality, because the quality is basically dictated by the shell growth. If the shell suddenly grows and there is a decrease in shell growth, all this non-uniformity creates problem. So, the shell growth should be controlled, and it is dictated by what? Dictated by the heat transfer within the mold. Within the mold, shell is very thin. So, all the more necessary to have a controlled shell growth through controlled heat transfer. This is an important requirement. Now, the shell, when it is the strand is just coming out of the mold, what is happening? It is very important to understand. The solid shell should have adequate thickness and strength at mold exit. Please try to see what is happening here. The shell is slowly increasing in thickness as it is coming down the mold. When it is coming just out of the mold, that is the exit of the mold, the shell thickness has to support the ferrostatic pressure from liquid steel. Otherwise, what is going to happen? The whole shell will snap, whole shell will puncture, and there will be a catastrophe, there will be a breakout. So, the whole casting operation has to be interrupted. So, this thickness of the solid shell at the exit of the mold is extremely important. If it is not adequate, if the strength is not adequate, it cannot withstand the ferrostatic pressure. So, there will be rupture of the shell, there will be breakout. So, that is why I was telling the growth, heat transfer finally will tell you whether the solid shell should have adequate thickness and strength at mold exit. Strength depends on what? Strength of the shell depends on the thickness as well as what is the type of shell, whether it is delta or it is austenite, because is a high temperature strength and toughness, they are different for delta and austenite. So, this is also important, that is why. Now, how the shell grows, what is the relation with time? This is called parabolic relation between shell thickness and time. This is very important to understand. If the shell thickness is y and the time is small t, the shell thickness is equal to some constant into t to the power half, 0.5. Now, this k depends on what? This constant? It depends on many things, depends on the heat transfer, basically it depends on the heat transfer. So, normally it has been found that during continuous casting, this rate constant capital K varies between 16 to 27, around this figure, millimeter root over minute. Why root over minute? Because time is in minute, shell thickness is in millimeter. So, this has to be in millimeter root over minute, minute to the power half. So, if k is known, you can find out with time how the shell is increasing in thickness. Now, sometimes how do you know k? For knowing k, there are two ways. One is a modeling of heat transfer. If you know the heat transfer, different characteristics of heat transfer, you can find out capital K, or whenever there is a breakout. So, breakout is happening at a certain location. So, you try to see what is the thickness. You do not want breakout, but suppose breakout has happened in a particular instance. So, at what level breakout has taken place, you just to try to see what is the shell thickness. Then you know at what length it has taken place, means the T is basically what? Length of the shell divided by the casting velocity. So, if you know L, that means the depth, at what depth breakout has taken place, at what depth the shell thickness you are thinking about. You know the casting speed V, T is basically L by V. So, either you know time, at what time after what time the breakout has taken place, or if you know the casting speed, you know what is the length, what is the depth at which shell has ruptured. So, you can find out the shell thickness, and if you know Y and if you know T or L, so you know K. So, that is the way you can find out K. Without modeling, what is the way of finding out K? That is a rate constant. I have mentioned here L is the length of the shell and V is the casting speed. Length of the shell means at what depth, vertical depth you are looking at the shell, that is what is important. Now, what is the growth rate of the solid shell? This is again important. This shell is increasing at a particular rate. This is del y by del t. So, it is basically, if you differentiate this equation, so 0.5 k into t to the power minus 0.5. So, the rate of growth of shell R is basically one can find out if you know what is k. So, at what rate the shell will increase, this is very important. Shell growth is very important, because this has some implications on the what will be the crystal sizes, what will be the dendrite sizes and all this. So, growth of shell is basically dependent on the heat transfer. Heat transfer is finally determining K. Please try to remember. If you have a different type of heat transfer in the mold, you have different type of shell growth. Now, heat transfer with if you have a oil lubrication, you are using oil as a lubricant, heat transfer is slightly higher. If you have a powder lubricant, that means the powder is melting, there is a liquid slag is solidifying, there is a solid slag. So, because of the solid slag, heat transfer is controlled. So, you have some other heat transfer. So, K depends on the type of heat transfer in the mold. Please try to remember. So, initial stage of solidification is important, because where the solidification is starting, quality is basically dictated at this stage also. The surface is being, because once the surface is forming in the mold only, afterwards the surface does not change. What changes? Subsurface and internal quality. The surface quality is dictated by the initial stage of solidification. Please try to remember, that is why initial stage of solidification within mold is very important.